Hello, welcome to Material Science and Metallurgy course. I'm Chandrasekhar, Associate Professor at Nallamala Reddy Engineering College, Hyderabad. In this video, we will be discussing about first chapter, Unit Outcome 3, that is, identifying the dislocation and strengthening mechanism. Let us discuss an important topic in material science called as strengthening mechanisms. Essentially, the question is how to strengthen a crystalline solid. By strength here, we means the mechanical strength as measured. Let us say by uniaxial tensile test, which will give yield strength, or an indentation test, which will give us hardness. These are measures of mechanical strength, and in many applications, higher the strength, better it is. It can carry more load, or it can be used for reduction of the weight because of smaller cross-sectional area can carry the desired load. So, how to strengthen materials? What we have been discussing now, that the dislocations make the crystal weak. So, one can think of a way of strengthening as simply remove the dislocations to make them stronger. Dislocation actually appears in the crystalline during production and fabrication processes. So, dislocations naturally present in the crystal during production time. So, this suggestion is not practically because you cannot really make dislocation free crystal. Careful experimental control can sometimes produce dislocation free crystal, but that is done on laboratory scale and in a smaller crystal, and it's not a very practical. So, remove the dislocation is not a practical suggestion. The other alternative is to the plastic deformation is happening because of the motion of dislocation. So, if we can obstacle the motion of dislocation, so various kind of ways have been used in engineering to achieve such kind of strengthening. Here you can see four types of strengthening mechanisms. First one is strain hardening, second one is grain size hardening, third one is solid solution hardening, and fourth one is precipitation hardening. Let's look at strain hardening. We know stress strain diagram, and we see that if we apply stress and trace the stress strain of some object, initially it deforms elastically and it remains straight line in the elastic curve, and then it becomes non-linear and plastic deformation begins, and we continue the plastic deformation right up to the fracture point. But let us stop the test much before the fracture. Then we unload the specimen. Unloading is found with the parallel line. We loaded and unloaded. This much residual plastic strain remains in the material. Suppose, since this has not broken, in case we repeat the experiment on this, what will happen? Now we are retesting the loaded deformed sample. What we'll see is the slope of the stress strain curve does not change, which means that after deformation it will show a higher yield strength than the undeformed specimen. So that is called as strain hardening. Let us think of it in terms of dislocation. So we have already seen that plastic deformation increases the amount of dislocation density. And we have also seen that is how the dislocation weakens the crystal. So this shows deformed crystal should be weaker. But we have seen this is not true because experimentally deformed crystal is stronger. That's what we called strain hardening. Now let's see another example of strengthening mechanism. Let us talk now about the grain size hardening. If you have a single crystal, then all the unit cell in the entire samples are entered in the same. So we have only one crystal. But the real crystallines are mostly polycrystalline. That is, orientation of the unit cell changes from region to region. This change in orientation creates what is called grain boundaries. So, grain boundaries act as an obstacle to dislocation motion. Here we have shown that you can see the grain size is larger here. First example, then in the second example. Here we call coarse grains and here fine grains. So fine grains have more grain boundaries and more obstacles to dislocation motion, which means higher strength required. Grain size means intercept size. Now let us discuss another strengthening mechanism called solid solution hardening. In the last video, we have discussed interstitial and substitutional defect. In both kinds, the solid solution always stronger or higher yield strength than the pure element. This is what we call solid solution hardening. Let us look at why is this. So, this schematic solid solution, we have this pure element where all atoms are equally sized. Suppose substitute controls atoms by large atom. So this is a substitutional solid atom and this is interstitial solid, and then these atoms have to move out and there will be a strain field around the solid atom. This strain field strain field of a dislocation. Now, let us discuss the precipitation hardening. Precipitation hardening, also called haze hardening, is a heat treatment technique used to increase the yield strength of the material, including most structure of alloys like aluminum, magnesium, and titanium, some steels, and stainless steels. In superalloys, it is known to cause yield strength, normally providing excellent high temperature strength. Precipitation hardening realizes on changes in solid solubility with the temperature to produce fine particles in impurity phase, which increases the moment of dislocation. Since dislocations are often a predominant carrier of plasticity, this serves to harden the material. The impurities plays a same role as the particle substance in the reinforced composite materials. Precipitation in solid can produce many different size of particles which have practically different properties. Unlike ordinary tempering alloys must be kept at elevated temperature for hours to allow precipitation to take place. This is called as haze hardening or precipitation hardening. Thank you.